So what I'm going to show here today, it's a lot of this, most of the stuff is not my own work. It actually is a work of the whole team. As you can understand, Earth system modeling is a broad and vast. So I'm not going to go into much. I'm going to try to describe in general terms the components of an Earth system model. And so here's the outline of the talk. And talk about how we can use space observations using the models to simulate the space observations, things what models can do for you before you actually launch the satellite. And then for each of the main components of the Earth system models, where do we expect the space can make a contribution, right? Primarily is an ocean color instrument meant for ocean color, but there's a lot more stuff that you can do with the OCI and the polarimeters. And I trust that you had a very comprehensive description of what the measurements can do, what they can retrieve, what's the information content. So I'm not going to go into much detail. But again, let's make that interactive. And I left some of the details out on purpose. And the main point here is for us to start a discussion and answer the questions. So models, right? We had, as part of this other project I'm involved with, which is called AOS, Atmospheric Observing System, a new satellite mission for the end of the decade. We have a modeling working group, and we had a workshop a couple of years ago. And the first thing is, you're always asking where models are going to go, where they're going to be. Because we have models today with the resolutions today, but things will be evolving. You are going towards more representation of processes, resolutions are increasing, and a lot of stuff we are today, it's not going to stand still. So here's more or less to give an idea what the community thought would be. The original models, certainly, they already are, but they'll be running the sub to 1 kilometers, very high resolution, right? Sort of cloud resolving in many respects. And the global forecast models will be 1 kilometer to 5 kilometers. We have global models today running in a sub 1 kilometer in demonstration mode. What we're talking about here, that the day-to-day forecast would be doing at those resolutions. Aerosol models, right, they are embedded in those. They also can be sub-millimeter 2 to 4. And for forecasting, 3 to 5 kilometers is probably what's going to happen. And the global climate models, ones that you run for centuries, would be at least 25 kilometers in the next few years. I think that is the sort of the tendency. Perhaps even higher. So the models do have more coupling. The physics would be advancing, right? New methods with more increased complexity, use of machine learning to accelerate some of those parameterizations and processes will be a big part of allowing that jump. And as more and more you reduce the resolution, the process is how they interact are important. So satellite data comes in then, is how those high resolution satellite data, typically, right? Satellite data are much higher resolution than what the models had. It turns to be that's no longer the case. Things are getting closer, and as you go towards process, that becomes very important. Okay, so here is very sort of high level. I'm talking about here the GEOS, what's the Global Earth Observer System, Earth System model that we run at GMAO. There's basically two Earth System models at NASA. One's a GEOS model, and the Model E at NASA GIS, where Brian works in, which is mostly concentrated on climate prediction. So here, this Earth System model, it has components for sea ice, so land ice, for the land, including vegetation. There's an ocean model for the physical ocean, for ocean biogeochemistry. And on the atmospheric component, you have the atmospheric physics and dynamics, right? Your weather, hydrodynamics. And you have as well full chemistry, reactive gas chemistry, greenhouse gases, and aerosols. And even aerosols, you can see here in the chemistry, you have several complexity of those models. You can have something, the simplest one is the go-kart, which is a so-called bulk model that only carries primarily the mass concentration, doesn't do much in terms of size distributions, but have several species, to a model scheme that actually represents internal mixtures, and there's more complexity in microphysical process, to even more detailed karma model that has detailed cloud microphysics. All of those are more expensive, and if you go to higher resolution, you tend to reduce the physical complexity, right? So that's the tendency. So models, you can run them by their own, but if you want to do a prediction, it's very important that you use the satellite data or ground data, what you have to constrain the state of that model, right, so that you can do. And basically, data simulation started something in the 70s for weather prediction, right, the early experiments, are now found in pretty much any component or system model. For the metrology, for DVARs and all sorts of variabilities, for aerosols, for the land surface observations, for the ocean, right? So all the floats and all the chemistry, the constituents for NOxes, for CO, CO2, and ozone, and other gases, just meant as an example. And for ocean biogeochemistry, the box that is implied here, that's where pretty much PACE is going to have a special role of being able to constrain the functional phytoplankton types. So again, as I said, those models, the resolution are collapsing. We are now able to run those models, resolutions at 1 kilometer, 1.5 kilometer globally. Couple ocean atmosphere models at 4 kilometers, and even something here with some of the chemistry at 3 kilometers globally. Those are proof of concept showing we can run. Some of those integrations here, they require about 30,000 or so cores. It's not something that we can run on a day-to-day, that we can do all the experimentation that we need to do it. But that's where we're heading, right? So we always have those demonstrations. And when you do, the other use of those high-resolution simulations is that they can be used to simulate observations, especially for missions yet to be launched, right? So, but that is really where we are going. You can see they are very sort of more and more realistic as you increase resolutions and processes. Yeah, that's another illustration of the same thing. That's the mirror reanalysis at 50 kilometers. Clouds were just sort of big sort of, blob of things. And here's a satellite image. And I'm going to show next, like 3.5 kilometers, you can see that you start to gain a lot more of the realistic features that you find in nature. Not saying that those models are perfect in representing the clouds, but they look a lot more what you find in nature. Okay, so let me just sort of go through a few. Here's an animation. That's one simulation. Actually, is the one before the 1 kilometer. I didn't have the animations for those readily available. I just grabbed those older 7 kilometers. And here you can see a global simulation of the cloud field, right? The visible clouds, and some representation of dust, sulfate aerosols, and organic carbon on a global scale. Right. As you progress in the next animation, show you a more focus on, there's no clouds here anymore, just showing that several species of aerosols that was represented in that run. You can see here the dust being emitted by the Sahara, dust from Australia. You can see the Asian dust. The right seasons, you can see here the dust coming from the Patagonia, right? The great fertilization of the Southern Ocean. And one of the things you get from those simulations is the realization aerosols are really, it's not one type, right? It's not one thing. And very often, cases you can find one aerosol type, but very often you find really a mix, right? A mixing state. And many times when you try to talk about aerosol types, is a really well-defined thing, because not always you have a clearly defined one type, you have a mixture. So that makes the problem actually complex for data simulation. I'll talk about that a little later. Yeah. It's very simple. Those plots are the simplest things that you can imagine, because you have, for example, one two-dimensional gridded field, right? At that resolution, for each pixel, you associate an RGB. And you have one layer. And then you just put all those layers together. And you just do that with transparency, right? Not only it has the color, as you go to higher one, you make it, a little less transparent so you can see. It's not as hard. It's really not as hard. The main thing is to come up with a nice color table that you like. That's where you spend all your time. You all make plots, right? So the main thing, those models have aerosols connected, coupled to the meteorology, right? And that coupling happens in two ways. One, aerosol exerts a radiative forcing on the atmosphere, right? The direct radiative effect, right? So aerosol particles can scatter, they can absorb radiation, and every species aerosols would have different optical properties. So in this plot here, we're just focusing on that 2017 hurricane season. All I'm showing here is aerosols, but again, you can clearly see the hurricanes. Why? Because the blue one here represents sea salt. And sea salt is very short-lived, and the emissions of sea salt are related to the wind speed, right? So every time you have a tropical storm or something with very high wind speed swirling around, they become a very good tracer to actually show the hurricane. So in that season was a relatively active system. You can see how much dust from the Sahara, for example, interact with the aerosols, how they can get sort of caught in those swirls, how they can get removed. And the dust and aerosols also have effects on the cloud microphysics, right? For example, dust, there's several studies that can show it can actually invigorate the storm by providing heating and entrainment, and the clouds get higher and stronger. And in some ways, it can also suppress. And what precipitation does, right, is the main sort of washout effect. You can see as the dust encounters some of those storms, they will disappear because they will really be washed out. So it's that sort of interaction between the systems that is important to capture. Yes?
Does the model calculate just the aerosols in the atmosphere or also deposition fluxes?
Deposition fluxes are one of the diagnostics, because once you try to model the aerosols, think about a mass continuity equation, right? You have a certain amount that get transported, some get in by emissions, and some get lost by washout, dry and wet deposition. So as you do that, those things they are diagnostic, they are output of the model. But they are not directly observed, right? But it's consistent if you try to understand your mass budget aerosols. They only there are estimates of those, but they are sort of in the second category. It's the same as in a meteorology model that assimilates temperature and moisture. They give you diabatic heating, right? But that's the sort of in the second category. It's sort of physically consistent with what you have, but you do not observe the diabatic heating, right? What is it? Oh. Okay, so here I'm just focusing on another type of aerosols. Those are sulfates, right? Just to give you a more insight on how sulfates are emitted from volcanoes. You can see those perennial volcanoes here on the Aleutian Highs and how they get transformed. And once you have, the emission of volcanoes are primarily SO2. And SO2 gets oxidized with OH and can form sulfate aerosols, which are the actual particulates, or also in clouds by aqueous production. So this plot here shows both. This sort of rainbow color is the SO2, which is the gas, the direct emission. And as they get transformed, you can see at the tail of those plumes, you have the SO4 extinction. So it's important for being cloud condensation nuclei affecting the brightness of clouds and all of those, microphysical, processes. But of course, SO2 is also emitted by volcanoes, is emitted by smelters in Chile. You can find those in here, by pollution in general. Although the good things in later years in the US, because industries have been installing scrubbers, the amount of SO2 had really going down to the point actually it's very hard to detect them from satellites. Other parts of the world, not so much, but I think that is the tendency that SO2 can be put under control if you really put your mind to it. But of course, that's not a scattering aerosol, right? It has a cooling effect on the atmosphere. If you think in terms of the warming of the planet, right? So it's like we're on borrowing money here. Once you take those scatters, actually you may warm, right? At least in the direct things, those things are. They're not good for your health. They really should be controlled, but they are not really solve your global warming problem by removing them. So here are a few words about, there's also effort on the simulation of CO2 and the whole carbon cycle and carbon fluxes. I have a few more slides later on. And here is just the evolution, the CO and CO2 here in the same plot. You can see the CO is mostly over the Africa in the biomass burning. And you can see here the evolution of the CO2 for this period of time. You can see the oscillation due to the seasonal cycle in uptake by vegetation and so on and so forth. So modeling of the carbon cycle, understanding the fluxes in where the carbon is going is something that's really important. And a great effort is putting and trying to understand, and to what extent you can have satellite data constraining some of those processes. And PACE may be able to do something, contribute to that as well. And here are currently, they state in our systems, other gases that you cannot simulate, but that's what we're doing currently. You have CO, NOx, ozone, CO2 for the greenhouse gases, the main instruments. And that's what I put here at the PACE, because people have already explored the possibility of getting NO2 from PACE, maybe some residual information about ozone. And there is also possibility for, at least for strong gas leaks, that one may be able to extract some information about methane, right? It's not an instrument that was designed for this. Don't expect that to be a trace gas instrument. But there is information out there that can be mined and probably used to complement the global observing system. I've said a few words about coupling, and depending on the time scales, but even shorter time scale, even for weather predictions, become more and more clear that the ocean and the atmosphere are a coupled system. And here's a typical example is for hurricanes, right? If you have a atmospheric system where the surface temperature is prescribed and doesn't change, your hurricane comes through, it doesn't deplete their warmth, right? It doesn't really cool the ocean, have this infinite source of energy. Once you couple the model, you can see as the hurricane go by, you actually leave a wake of cold water, right? It's just, so it's really becoming, even for shorter time scale, that really this coupling is necessary. And weather prediction and data simulation direction everybody's going to is to start doing the problem of the ocean, the atmosphere, even for the shorter time scale. Not much about season prediction here. So far, most of it is related to the ENSO timescales, right? And predictions are typically 6 to 9 months. And they are, because as you know, atmospheric predictability, the initial condition of the Earth doesn't really matter, right? You're way beyond the predictability limits. However, once you couple to the ocean state retains information much longer, right? So a lot of those seasonal prediction problems, the initialization problem, the data simulation that becomes important is the ocean state. So you have to do ocean data simulation, and is the simulation of the land, which also has a much longer, time scale. So that's a couple of slides that I got from my colleague Cecile Russo. Cecile used to be a GMAO. I think now she is in the ocean biogeochemistry group, but she's still working with us. She's still part, of the family. Right, that was the whole idea, right, to make sure.
And many of you met her yesterday as one of
Yeah, so another component of that model, so the ocean that we talk about weather prediction, that's the physical ocean, is the temperature, salinity, and the currents and the fluxes. But there's another component of the ocean, very much like, say, the chemistry runs off the atmosphere, is the ocean biogeochemistry, right? Which actually is important for the and the ocean is called the NASA Ocean Biogeochemical Model is NOBM. So Watson Gregg developed for many years, and Cecile made a lot of contribution to it. It represents here a number of functional phytoplankton types. I think it's about 7, if I don't. And they have coupled to this a very detailed ocean atmospheric spectral irradiance model as OSN. You can actually simulate ocean living radiances in several wavelengths, and in particular the wavelength that PACE is going to be retrieving. Right? So this model has been validated about multispectral ocean color data sets, and it has been used to simulate actually PACE observations. I will show some of the results from my colleague, Patricia Castellanos. So, and the NOBM also has a data simulation component, right? And it brings in all those elements of data simulation where, for example, you can take satellite data, which is somewhat sparse. You can assimilate that into an ocean biogeochemistry model, and all of a sudden you have a global, continuous, space-time continuous data set, very much what we had for the atmospheric reanalysis. And there's a lot of effort in developing the system for the PACE measurements, right? That is right, the bread and butter of PACE is to provide that kind of constraints for ocean biogeochemistry models. OSSIS. That OSSIS stands for Observed System Simulation Experiments. Is, I think everybody, many people may already be familiar, but it's really the device to simulate the measurements to a certain degree of detail before the instruments are there. So just a definition for the experimentation observables, right? Whatever you're going to measure from your satellite, are simulated from fields by our Earth system model, a comprehensive one. So if you want to generate measurements that are sensitive to ocean biogeochemistry, your Earth system model has to include a component that that has ocean biogeochemistry. Otherwise, you cannot simulate your signal. And when you do those simulations, you do that for a set of goals. For example, if you think you're going to be using PACE data in the future for doing ocean biogeochemistry predictions, you can simulate the measurements, you can assimilate the simulated measurements and see how much impact they have in your biogeochemistry prediction. But that's the traditional sort of forecasting use of OSSIS. Another use is to test retrievals, right? Because you can simulate your radiances, right? And add the footprint of the satellite, all the channels, and provide to the ocean atmospheric correction, aerosol algorithms, or what you have, and say, all right, do you think you can retrieve? Here is the radiance that I simulated. Let's see what you got. I know exactly what I put it in. And now you can do a more sort of systematic error characterization, understands, and hopefully not meant to show where the model is wrong, but just give you ways of understand where we're missing, how you can improve your algorithm. So an RC usually, I'm not going to talk in detail, it needs a nature run, which is basically a high resolution, the highest resolution comprehensive representation nature you can have. You need your simulator, right, that can simulate the radiances or the retrievals. You have to spend some time with error modeling, right, because those measurements are not perfect. So you have errors in the forward models, you have errors in the instrumentation. Usually instrument model needs to be built in. And then you have applications for the diagnostic sensitivities and the forecasting, the analysis or reanalysis I was talking about, or the quality of the retrievals. So there's a really, it's an involved process that actually tries to bring everything together. And typically when you do the simulation before launch of an instrument, is very useful in the sense a lot of the building blocks that you need to assimilate the data when the satellite comes down has already been developed in doing those simulations, right? So we are really indirectly preparing for making use of the data when it comes down. So here is the few slides from Patricia. So you have an Earth model with ocean biochemistry, atmospheric aerosols, and trace gases, right? As I showed you. You compute the ocean surface radiation and the top of the atmosphere radiation, right? So that's using the OSM model to do the calculation from the model fields. Not going to go into the details. You will have the slides, and some of the references are here. But again, you simulate the water leaving radiances, right? So whatever from the ocean state, you can have the water leaving radiance. Now you have all those aerosols suspended in the atmosphere. They're going to mess you up, right? They're going to be absorbing radiation in this stuff. Things are going to get entangled. And you end up at the top of the atmosphere radiation. And that's where the algorithms for atmospheric correction, aerosol retrievals and stuff come in. And they try to retrieve or estimate what the atmospheric contribution is, what's the ocean. In a simulation environment, you know what you're putting in, right? And then you can see to what extent you can retrieve that information. Great as space is, as satellite data is not really a perfect instrument. It doesn't really have all the details that you need to actually solve the inverse problem. Approximation needs to be made, and so really is, that's the main use of that, is to understand the limitations. A few examples here. That is the case. Patricia took a little granule here in the middle of the Pacific, and that's the total top of the atmosphere reflectance. And here's the surface reflectance that was put in at 500 nanometers. And that's the aerosol optical depth. That's the atmosphere, right? So here you can think about the top of the atmosphere is the sum of the surface plus the aerosols. And you can see a lot of the aerosols are modulated by the relative humidity, right? I didn't talk about that, but it's not only the dry mass of the aerosol that matters, but high humidity, hygroscopic effects makes the aerosol to be larger, change the size and the optical properties. And sort of, just to show here a lot of that variability actually comes from. And to the next slide, I think is here is basically the AOG that we put it in, and the different algorithms or variations of aerosol algorithms try to retrieve this. And you can see some of them have this blob in here, which is actually contribution from the surface, right? So the algorithm got a little confused. Algorithm number 3 here, I should have a blind date. It's just more a point of illustration here. It's not a shootout which one is better. For all that I know, things have been already addressed and those things work just as well. Is some of them actually perform better, right? And the indication here, there are some surface contamination that needs to be addressed, and people can actually explore alternatives by having sort of that device in front of you. Here's another example for, it's just the spectra, right? And here is the one, the ground truth they put from the model, and here is the OSI reflectance. The spectral shape is very realistic. There are places where it overestimate, other places underestimate. And the reasons for that is part of the algorithm development, understanding what are your assumptions, what's affecting the discrepancy. And there's a number over here. Maybe the assumptions in the model in doing this calculation, maybe that's what's in fault, or actually what's assumed by the retrieval may be more realistic. It's a starter conversation. It's something that gives you an objective way to analyze those differences and try to trace them back, and in the process understand what you're doing. So here's another example. That's the chlorophyll that we put it in, and that's the chlorophyll that was retrieved by one of the algorithms. As you can see, the gradients, a lot of this stuff is realistic. There are regions here, regions of very low chlorophyll that get a little overestimated. So what exactly is causing it? So you have now a device to dig in and try to understand your algorithm. Right, a lot of those algorithms, you can do sensitivity, you can do Jacobians, right? So you can do how much each one of those depend on your inputs and analyze it and understand it and exploit. Aerosol data simulation. As I said before, aerosols are very complex, right? In some ways, the chemists have a much easier problem, because once you have a CO2 or CO molecule, it's a molecule, right? The absorption properties is relatively well known. You can go to the lab, you can make measurements. There's no shape for a molecule, right? There's no types of CO. There's not the green or the blue. There's one thing, it's just one molecule. The aerosol problems are a lot more complex, right? Those particulates, you have different types. You have dust, you have sea salt, you have smoke. If that wasn't enough, they have different sizes, right? It's not only the mass of them, but it's the size. They have different, index of refraction, right? Each one of them. And they are not constant, they have shape, right? You can have spherical dust, if there is such a thing, or you have very amorphous, which complicates a lot of radiative transfer. So it's a much rather or less observed problems. It's very really. So the models usually represent 3D concentration. A simple model only has the mass. Model schemes will have the number concentration, right? The number of particles. Not enough to have a certain mass, but you have fewer or more particles. And a more sectional detailed schemes will have very fine bin microphysics for each size bin, very expensive. The other difficulty here is the emissions, right? So sea salt and dust emissions are typically a function of the soil for dust and the mineralogy, and the wind speed are dynamically determined. Fires can be detected from space, and the whole fire emission estimate is also a very challenging problem. There's a lot of things you can find. The fire location, that's the easiest one, but how much constituents are being emitted is really tricky. But anyway, that's a big thing. But the main thing is, if you are observing mass, you are measuring something like optical depth or an optical property, you really need an operator here, which are the aerosol intrinsic properties, the index of refraction, the mass scattering efficiency of what you have. That in modeling data simulation these days, we pretend we know, right? There's something called a mythical dust that has one index of refraction. Unless you start to resolve mineralogy in the things, you don't really. So what you do, you pretend that you know those parameters, and basically all you have to your disposal is the mass, and you can add or remove mass. But again, that is a really not ideal. As you move forward, and you have instruments that give you to the spectrum more information about size and index of refraction property, we have to now to also start to assimilate and to constrain those parameters in ways that we have not been doing. I'm going to close here. So most of the time now people assimilate just AOD at 550. There's one parameter. If your AOD in the model is too low, you take out mass, right? Otherwise, it puts out mass. And you do that without really being able to represent too much about the species. That's what I was from black and white TV to a color TV. Okay? As you have now multiple wavelengths, you have spectra, you have polarimetry, we start to gain a lot more information about the different sensitivity about the aerosol types. And you are able now to make corrections on individual species. Not entirely, precisely, but you do have that information content. So that's what we look forward to PACE, is the spectral resolution. I think Lorraine, you guys had description of the algorithms. The amount of extra information that we have today, we'll have with PACE in the polarimeters that allow us to much better constrain the aerosol state. And so I'm almost done here. So what we do is, especially for the forecast, but we really have a time problem. We haven't really been using Aeronet. Probably no one described Aeronet, which is a network of surface stations that make direct measurements of aerosol optical depth is our sort of validation standard, calibration standard. And today, I not only use that for validation and calibration, but also we simulated on that data. It started as having different retrievals, each one with its own strengths and limitations, and trying to use AeroNet as a calibration standard by correcting the retrievals. At one point, what we ended up doing, so long sort of torsos, is that we could use the reflectance directly in using machine learning to actually to retrieve those optical depth at different wavelength. Here's an example. And therefore, instruments such as MODIS, VIIRS, and the geostationary can be sort of homogenized and be trained to be giving, for the location of the AeroNet, something that is consistent and biased. So a lot of the, for operational applications, if we can have the latency of the level 2 probably may not be there. If we can have the level 1, maybe a cloud mask, there's a lot of things we can actually use that in real time with this approach. And of course, there's other observing systems. I'm not going to be talking much about surface stations, surface PM 2.5, which is really what's matter for air quality. It's a very tricky measurement to use because they're often really not at a scale that you are modeling. It's also a single level. And the vertical structure is really what comes in the LiDARs. The LiDARs, they are in development and emerging. But that's nothing really to do with space. So carbon study, that's really my last slide here, and for my colleague Leslie Ott. So NASA modeling is a very much integrated carbon modeling, which really is a data-driven modeling approach. You got satellite observations of the ocean color, the fire intensity, and the vegetation greenness, right? And you integrate that with atmospheric models, and you basically use satellite and on the other end to measure or validate what you have. Data simulation is the same way being developed for the greenhouse gases in carbon cycle modeling, which involves the ocean component, the terrestrial component, is very complex. Space, what is space can offer? Space is for the ocean, but again, luckily, they're not going to turn it off when it goes over land, right? Still. And GPP, global productivity, can actually be estimated from the space spectra, and those things really would become a very important input for not only for the greenness, but actually the productivity, vegetation productivity over land from the space spectra. I think people like Joiner at Goddard is really very much interested in using this data set for this terrestrial component. So not designed for it, but I think it's going to be a good thing. So in summary, sorry I didn't really go into many details about too many things, but it's basically the main components, right, that you can make contributions are for the atmospheric constituents, for aerosols and some of the reactive gases. I should have put greenhouse gases here in the quotation mark, perhaps for some methane, strong methane leaks. It can have something to say, still to be demonstrated. From the ocean biogeochemistry is the primary contribution. And on the land surface is the vegetation, right? Is the primary productivity over land that can be in. So there you have it. So if you have any questions, you want any discussion, just take it any direction you like. Right.
So I guess my question is, I guess atmospheric correction would currently use the best idea of what the atmosphere is, and maybe your model would use a similar idea of what the atmosphere is. And so does that bias the results if you're, say, doing atmospheric correction on a model that's already your model that you inputted? And it seems like it would give you better results than what would really happen if everything we know is already used in atmospheric.
Right. You're talking about the incestuous problem, right? That models tends to be more similar yet different, right? So if you have, so an atmospheric model would have a lot more dynamic viabilities, a lot of stuff that brings in. But again, you need to make assumptions about, if it is dust, what's the index of refraction, all of those things. If your atmospheric correction and the thing makes the same assumptions, that you have over there, yeah, you're throwing a softball, right? So again, what you can see when you do this realistic simulation, you still add a lot more realism that you cannot assume in your algorithm, right? And so the approach is, if it doesn't work there, you're not going to get any better. But don't oversell, right? Don't use that as a marketing device, just because things tends to be a lot easier to do in simulation mode. That's a constant worry. It's a very good point. There and there.
As model resolutions improve, what are the spatial scales that you're finding both in atmosphere and ocean that have distinct differences in model output? Are there spatial scales that, when you get below 4 kilometers, 1 kilometer, that really matters?
Right. Right. So, right, there is this so-called, let's talk about sort of clouds, right? That is the large-scale models, right? Say 10 kilometers and above in the climate models. Everything's parameterized. You do not resolve clouds, right? Clouds do not happen at scale. And then you have to 1 kilometer and sub-kilometer, when you start to resolve cloud physics. Okay. Then what happens in what's so-called gray zone, right? When you go from 10 kilometers to 1 kilometers. Things do not start to resolve in one day. There are some cloud systems, right? Organized cloud systems that you can resolve at, say, 5, 7 kilometers, but not the very small popcorn cumulus or the trade cumulus and that kind of stuff. So, and that really is a big challenge, because we cannot jump altogether to do sub 1 kilometer globally. So how do you transition from not resolving, say, convection to starting to resolve convection? New parameterizations, they are what they call scale aware. They try to estimate when they can resolve that process. So therefore, you let the physics speak, and when you have to parameterize. Some others, you try to specify that in others, less sophisticated models. That's really the million-dollar question. It's really hard. Gosh, you are asking a question that I'm not really qualified to resolve. But I think there's 3 resolution. I was talking to Andrew Malad, where you start really to have the ocean mesoscale, right? And how that is actually interacting with the mesoscale in the atmosphere. I would just go in here and say that about something like 3 kilometers or so, it just gives you a very good representation of the ocean eddies. But I think some of those echo models out of JPL, those guys are even going 1 kilometer globally, right? So for more and more, resolution. So yeah, so that's what we like to be. Even when we can make those runs for a demonstration, we are still not there. We need to learn how to live in this sort of gray zone as you transition. Yeah.
Once you are happy with your resolution, which processes would you target to, would you prioritize to target, to improve model predictions or reduce uncertainty?
Right. That's a tricky question. I'll tell you why. So from a pure physical point of view, right, you start to say, if I'm going to go to that scale, starting to resolve clouds and cloud microphysics, then I have to make sure my cloud processes you go into the detail and you resolve them. Very often, errors come in pairs, right? And as you start to become more and more sophisticated, it doesn't mean your forecast is going to improve, and very often it does not, right? Because once now you're doing something right, something else has to be done right too, right? It's a sort of package deal. You cannot. But mostly, and again, that goes with the design observing systems, right? So the other project Brian is involved and I'm working with is the AOS, Atmospheric Observing System, right? It's just related to aerosol cloud convection and precipitation, and also to come up of the satellite measurements that would allow you to diagnose those processes so you can actually measure them on a global scale. And how do you diagnose and stuff is still something we are learning. So I would say if you are a cloud physicist and stuff, you focus on those processes, right? So if you're doing something else, in the aerosols, you start to upgrade also your aerosol microphysics, how interact with the clouds, and be realistic that it may be a bumpy road until we can actually show. Like, that's the difference sometimes about doing research with a climate model. You can play something, understand the physics, and you can write papers that are very good papers. Maybe the model is really bad, right? But if you are in an operational house where you have to put out forecasts, you cannot really promote an upgrade that is in fact a downgrade, right? Because other things that, that is not quite working, your forecast still degrades, you don't do that. So the whole sort of operational stuff is really tough because many features that we have, we know is physically correct, but we haven't been able to promote because we haven't made it to be able to work in a holistic way. So that's life.
If you're trying to do data assimilation, what happens when, I'm thinking about the Southern Ocean, which is cloudy a lot, and it's hard to make retrieval pretty often, so you have a bias in where you have information and where you don't. What do you do with that situation?
That is, that is, we just live with it. But again, or you try to find ways that you can complement what you have. In the old days, right, talking about the 70s, the main observing system before satellites were radiosondes, right? You only observe things over land, well, twice a day when you had them. And eventually, satellites came in, and the initial use of satellite data for weather prediction, you stayed away from clouds. It was all clear sky. Recently, a lot of advances have been made, they call all-sky data simulation, where you use cloudy data, primarily from the microwave, and you try to, and that really has shown very promising results. Other ways to come up with measurements, right? They can actually be resilient to clouds for, microwave, for the aerosols. I was talking actually with the Aeronet to the CML guys, they made, asking what you guys need for the future, right? Do you need ocean measurements? And I said, well, think about if you could actually instrument the commercial ship fleet with some photometers, so you can have that from below over the ocean. That's a big gap in the observing system. But the question is, who pays for it, right? Who funds that? And space agents like NASA, we are. It has a strong suborbital, but that's not something necessarily kind of attraction. Yeah. Okay, you and me. Yeah. Okay. Yeah.
Is the data from the simulations then for space available to use?
Yeah. As far as I can tell, Patricia Castellanos is the contact. I think we put that on our. Not FTP anymore, but HTTPS, site. That data should be available, right?
Yeah, I believe she has.
Is it global? Like, or just for some regions?
For what Arlindo presented, it's that one granule with a
Yeah.
very, very, very good atmospheric nature run on top of it, which is
Right.
computationally intensive.
Yeah.
There are global simulated OCI level 1B, so top of atmosphere files. We have 5 days of global, but which we'll talk about a little later. But those are, for lack of a nicer way of saying it, relatively dumbed down. The models are much simpler to allow us to do
Right.
global.
Yeah.
I want to have you give me more details about the broad brushstrokes for the temporal range for ecological forecasting. So is it both something like base, like are we expecting forecasts on the seasonal scale, a lower temporal scale? And the second question, I don't know if it's related, but is
Right.
how would you incorporate like other methods, like Bayesian methods from already existing ocean color sensors into this forecast?
Right. Right. So the whole thing about data simulation, usually you don't do a base data simulation, right? Base becomes one more data source that goes as part of the observing system. For the ocean color, I'm a little bit out of my element here. So, but you do have, today you have some chlorophyll retriever from Modis, right? So I don't know if there's anything still done with the VHRR. All existing instruments, they're all there, and then Glimmer is going to come, and all of those things will be part of those observational constraints that you're going to have to enter your Bayesian minimization method, right? A data simulation is nothing more than a 3 or 4 dimensional Bayesian optimal summation, right? It's just the same, nothing. And the formulation is slightly different because priors may come from a model forecast, that kind of stuff. So you're asking about time scales. So for the ocean, ideally I want to be running that on a daily basis. And as in our seasonal forecast right now, we are not yet running seasonal forecasts for the ocean biogeochemistry. But if we would, if we could, if we decide, if we have the resources, once we are properly initializing, you have data, you can use that for seasonal forecasts, right? So for example, typical what people do every other day or every 5 days, you run a 6-month forecast, right? And that provides an ensemble in the future of all the possibilities. So there's nothing preventing that. And you could do that on a short time scale, because then you can think about the data simulation as this sort of device to invent data, but there's no data. Right? I like to think about it in many ways. I think it answers some of your question. What happens if there is a gap because of clouds? You can think about the model as a conveyor of past observations. Right? I simulated something today here that's clear, right? And that goes into the model, which has currents, and we'll transport that over that region that tomorrow is going to be, right? Of course, that transport is never perfect and everything, but again, you are conveying that past observations subject to the quality of the model to those unobserved regions of the atmosphere. And for the known ocean biogeochemistry, right, for the aerosols and stuff, my hope is that we'll be able to incorporate that for the characterization of aerosols, globally on basically every 6-hour forecast that we put out.
As you estimate that time to do that, are you doing parameter optimization?
Yeah. Yes and no. There's a whole process of bias correction for the satellites. A lot of the, as you try to do the analysis, you are sort of optimizing some bias parameterization for some of the instruments. For the aerosol problem that I showed you, basically I implied that that's what we need to do, right? Because some of what's now parameters, meaning parameters means not something that we evolve dynamically, right? For example, the index of refraction of dust and stuff is something that is basically prescribed. And those things need to use the richness of the data and try to constrain that and give it some sort of spatial, perhaps even, temporal characteristic. No, it is not done, but, for the aerosol problem, absolutely, that's the next step. And the other parameter you can think is for trace gases and aerosols, emissions are a big thing, right? So we do parameter estimation for the biomass burning, and how do we convert from the fire radiative power to the actual emissions, which is gram per kilogram of consumed carbon. Those are the parameter estimation that are done in that respect. So, yeah, I think it is inevitable that we're going to have to go that way. Okay. Okay, so let's one at a time. The first one was?
The first one is how do you think the PA will help with the model bias?
Right, right. So that is, you can think about in a data simulation process, right, as DDT of a given variable, right, is the transport, is the physics, so on and so forth. And now you have this delta term, which is a correction by the data, right? You can think thermodynamics is just as another force in term, another tendency, for that model. Without going into details, actually, we wrote a paper about that in the late 90s about all of those data simulation, retrievals as well, right? Everything is done under the assumption of no bias, right? Which is not true, and we know that's not true. And we have developed algorithms that can jointly estimate the model bias and the bias in the observations. But it's commonly not done, right? So everybody, like the retrieval and stuff, because there's a lot of mathematical simplifications, computational simplifications that you can do by assuming the observation not biased and your model prior is not biased. Even on that, even without using this bias-blind algorithm that we talk, you should make a contribution towards the bias. For example, if you have what they call analysis increments, right, is the difference, how much correction the observation makes, say, to the result optical depth, right? So if you make a monthly mean of that, right, you can see there's a systematic correction from, and that basically is the, one of the bias in the model, right? And you can use that. It turns out if you do that rigorously, that's actually is an underestimation of the bias, right? It's actually a little lower. Bias will be probably higher. But it is, so in practice, there is a bias correction that implicitly that takes time, but it's not really perhaps the full extent in which that bias can be corrected. And the second question?
The second question is how do you plan to deal with the AOD error correlation?
Right. Right. I was debating if I was to put that slide. So, I was talking to Brian today. So we are, in the way we are approaching this, right? So we have a neural net algorithm, right, that takes you the reflectances, and we use AeroNet as the training reference, and you get the AOD. One of the things we have been working on is something called evidential deep learning. What evidential deep learning does, how can I explain that in a few words, is jointly estimate, say, the AOD, but also the probability distribution of the AOD. So you have systematically, you estimate what the observation error is. As I state dependent, not a number, right? It's not 0.01. For that particular case, for the particular type, it learns how to estimate there's something called aleatoric and epistemic error, which has to do with the systematic and random error that comes from the instrument. I have not demonstrated how well that's going to work, but that's the approach that I'm pursuing right now, is to use evidential deep learning to do joint estimation of the AOD and the uncertainty. Right. Yeah.
So my question is a little bit related to this second question. So we know that we are simulating the AOD from AeroNet, and the model usually simulating the mass of the error.
Right.
So you have a negative AOD with the mass by assuming the max extinction coefficient, for example. And that's based on assumptions. And so how do you make sure that your assimilation is got improved compared with the previous one? So how do you validate your assimilated results after your assimilation?
Right. Yeah. Well, so that's the whole dilemma. AeroNet was always held back, right? Because it was the, and a lot of the testing and experimentation, we hold back AeroNet as the, the gold standard. You do all the satellite data and make sure whatever we did moved us in the right direction. But what you're addressing here is the problem that I briefly alluded to, is the model is concentration, number concentration or mass concentration. And in going that to the optical parameter that you measure, AOD or reflectances, for that matter, you have to make vastly oversimplified assumptions that, but the promising thing here is as we move to those new sensors, right, with more information, we start to get from polarimetry more information about the index of refraction or constraints on the index of refraction, so that we can make progress by parameter estimation or whatever, and trying to get those things better constrained by the data, okay? So, but how do you, there's one sort of pragmatic way of putting in the forecasting problem is to test your ability to predict future data. Right? So I know if it's the truth, but there is AeroNet today. Can I predict AeroNet tomorrow? And that sort of, in a way, is the bottom line. That's a well-defined problem, right? Whether AeroNet is absolute truth or any other instrument's absolute truth, but just the ability that we can predict future data, that's what we try to keep ourselves honest.